Greetings. Welcome to Math 409 Lecture 31. Unfortunately, something came up and in class was canceled today, so I wanted to just quickly record a few short notes about a problem that we were discussing previously. So the problem was, given some triangle T, what are the maximum rectangles S and I you can construct? By that I mean we want the area of R plus the area of S divided by the area of T to be as large as possible. And so in class, we actually talked about a couple of different ways to prove that, there is a way to do this. And there is a really nice formula in the end where it comes out that the heights of S and R are the same, and they're both equal to a third. And of course, we have one way to do this is multivariable calculus. Another way to do it is through some nice geometry and cutting. Another way is to do this as a series of iterated one-dimensional problems. And once you do this problem with S and R, of course, the natural question is, well, what if we had three rectangles, or more generally n? Is there an answer? Would each of them have height, 1 over, where they all have the same height, for example? And one of the methods we did yesterday, last class, easily generalizes to that case. It gives us, we want to maximize or minimize the sum of squares given, a fixed sum. What I want to do is I want to quickly talk about how you could do this using just one-dimensional calculus. And so apologies for throwing all the math on at once. It's been a very, very busy, hectic day. And so what I want to do is just quickly go through the argument. So let's take our triangle, which without loss of generality, we can assume is isosceles, right? So these are 45-degree angles, and we can assume that the that the diagonal line is y equals 1 minus x. So we can call the points un, un minus 1, un minus 2, all the way down to u3, u2, u1. And so the last rectangle is going to have a length of un and a height of 1 minus un. The next one is going to have a width of un minus 1 and a height of un minus 1. And in general, it'll be down to u3 minus u2 for the height, and then u2 minus u1. So in the first level, the smallest rectangle, we try to figure out what's the maximum area we can get given everything else that's been done. So we have u2 minus u1 times u1. When we use calculus to find where is the critical point, we get u1 is 1/2 u2. Again, u2 and everything else is fixed. So the area of this rectangle is just u1 squared is 1/4 u2. And that's why down here, the first area is 1/4 u2 squared. We now look at adding the next one. And so the area with two levels would be the 1/4 u2 squared from before, plus then u3 minus u2 times u2. That's always going to have a second term looking like that. We expand things out, u3 u2 minus 3/4 u2 squared. And that comes from taking the 1/4 u2 squared and subtracting off the u2 squared. We take the derivative, set it equal to 0. We get u2 is 2/3 u3. So u1 is 1/3 u3. And we're beginning to see a pattern: 1/2 u2, 1/3 u3. The area of those two pieces is 2/3 u3 squared minus 1/3 u3 squared, or 1/3 u3 squared. And that's the 1/3 u3 squared term here. So the term is going 1/4, 1/3. Let's see what the next one is. So the next one would be our 1/3 u3 squared. That's the area of the first two rectangles, plus u4 minus u3 u3. So when you expand out, you'll get a u4 u3 minus 2/3 u3 squared. We take the derivative, set it equal to 0. u3 is 3/4 u4, and lo and behold, u1 is 1/4 u4, and the area is going to be 3/4 u4 squared minus 3/8 u4 squared is 3/8 u4 squared. So the next term is going to become a 3/8 u4 squared. We do a similar calculation for the next level, and we're going to get a u1 equals 1/5 u5 at the end of the algebra, and then we get that next one, the area of the first few pieces, is 2/5 u5 squared. So just one rectangle was 1/4 u2 squared. The first two rectangles was 1/3 u3 squared. The first three was 3/8 u4 squared. The first four was 2/5 u5 squared. So the sequence is looking like 1/4, 1/3, 3/8, 2/5. And so the question is, what is the next term on the sequence? Can you come up with a general pattern? So you should pause the video right now and see if you can figure out what is the next fraction in this pattern: 1/4, 1/3, 3/8, 2/5. So again, pause it here, think for a few minutes, and then hit resume. 5, 4, 3, 2, 1, resume. Okay. Well, a better way to look at this is to realize that we actually got some of these numbers by doing algebraic simplifications. When you're trying to deduce patterns, it is absolutely terrible to do algebraic simplifications to hide what's going on. These numbers that can be written as 1/4, 2/6, 3/8, 4/10. Running it like that, the numerators are just 1, 2, 3, 4. Okay, the numerator is just k, the denominator is 2k plus 2. And we can quickly prove by induction that this pattern is going to continue. If we have, k over 2k plus 2 uk plus 1 squared, the next area we add is uk plus 2 minus uk plus 1 times uk plus 1. We then do the subtraction. We set the derivative equal to 0. We get uk plus 2 minus k plus 2 over k plus 1, uk plus 1 is 0. So uk plus 1 is just k plus 1 over k plus 2, uk plus 2. And so we then get, exactly as before. It's now just going to be 1 over, some integer times, the first one. The only thing that gets a little bit different is at the very final stage, that's going to be k equals n minus 1. We'll have n minus 1 over 2n un squared plus 1 minus un times un. Because, we now have a 1 rather than a new variable. And so when we take the derivative, we get 1 equals n plus 1 over n un, or un is n over n plus 1. So u1 is 1 over n un, or just 1 over n plus 1. And so we see they all have the same height, and that height is just 1 over 1 more than the number of triangles. All right, have a great day all. Have a great Thanksgiving.